I'm going to graph the line that you guys should have, and then we'll go over the highlighting portion and make sure we understand that. Again, I understand our review. I try to go through a little bit quicker, but make sure everybody can still get their questions answered. And then I'll obviously walk around and help anybody individually that's struggling a little bit more. So your first line, I'm going to do the best I can. It's a little bit. Yeah, I don't really draw straight, do I? So you guys should have a line that looks like this, a y-intercept of 1 and a slope of 2. Okay. Your second line should have a y-intercept of 3.5 and a slope of -0.5, so down 1/2. And then your third line should just be a horizontal line at 1.5. Oh, so sad. Just ignore that one. Okay. So 3 lines, yes? Okay. Are we any questions about any of the lines that we had to draw? No? Okay, so then the highlighting portion. So what the highlighting portion was trying to tell you guys was parts of the domain. So those words are really important for understanding what's happening. So it said in graph number 1 to highlight the portion of the domain where x is less than 1. So try to remember it's talking about domain. So we're focusing on where x is 1 as if they're kind of building a wall here. So x less than 1 are all the x values on the left side of that. Okay? The point that corresponds to x being equal to 1 is this point on the line right here. If x's are less than 1 from here over, okay, we want the points on the line that correspond to those x values. So that would be that infinite number of points all along here. If you pick anything from over here, those correspond to an x value that's past the boundary and is greater than 1. So we should have highlighted this portion of the line. Okay? And it would end right here at this point, and I would keep that point open because the restriction didn't say to allow x to equal 1. It could only be less than 1, so I wanted to go all the way up to 1 without equaling it. So on a graph, we represent that with that open point. Okay? In graph 2, we wanted to highlight the portion where x is bigger than or equal to 1, and at the same time x is less than 4. So basically all those numbers falling between 1 and 4. So again, on our x-axis, here's a boundary of 1. Here's a boundary of 4. So if we think about between 1 and 4, we just want to include those x's. Okay? The point that's on your line that corresponds to 1 is right here. And the point that corresponds to 4 is right here. And all these points in between would have some x that's bigger than 1 but smaller than 4. Okay, so those are all the points we want. I drew the endpoints this way, again, because of the restrictions. X was allowed to equal 1. So at 1, I filled in that point because that would have an x value of 1, and I'm allowed to have 1. X wants to go up to 4, but it doesn't say in this inequality that it can equal 4. So at 4 as the boundary, I left the open point there. Okay? On the last graph, it said to highlight everywhere where x was greater than or equal to 4. So again, finding that boundary. Here's an x of 4. Here's the point that corresponds to that on the graph. And x is bigger than 4 would be on this side. If this is where x is equal to 4, all the x's bigger than 4 are here. So we want the points along our line that correspond with these x's over here. So we want this portion of the line. We're going to pause for a minute just to make sure everybody's okay with 1. Did you have any questions on how we graph the line? And 2, do you have any questions on why we highlighted which portions or why I left open circles or closed circles somewhere? So right now in your group, if you think everyone knows, quiz them, ask them, and see if you agree with their answer. I want you guys to make sure they understand why we chose the parts of the graph that we chose and why the endpoints are open or closed. So do that real quick. Notation is now saying everything that the sentence said above, but as you guys have probably noticed in your math career, mathematicians don't like to write lots of words, right? So they try to condense everything with symbols, notation, and all of this kind of stuff. So basically here we have those same 3 lines that you graphed, but notice they're all part of one equation. There's only one equal sign here, meaning this is one thing that I'm drawing. It just happens to have 3 different parts to it, and during those 3 different parts, it behaves a different way, right? So first it starts behaving like this line, but only in this part of the graph. Then it starts behaving like this line in this part of the graph. And then it starts behaving like this line in this part of the graph. So you guys have highlighted the exact portions of the graph. So if you take all those highlighted portions and put them together, we can get the graph of this function as a whole, right? So that's one strategy. It's kind of a long strategy, right? But if you really struggled with this, you could, every time you see a problem like this, graph each of these separately, highlight the portion of the graph that you want, and then bring those things together on one graph. Okay, that's one option of how to get a graph of these piecewise functions. What's another option that you guys have? You guys have experience with this, so you guys have some ideas. What's another way that we could get the graph of this function when they write it like this without having graphed every single one individually? Yeah. Okay. So you physically mark the domains on your graph, like the separation points. Okay, so what she's talking about is marking on the graph the separation points. So right here, we know that this one exists on one side of the number 1. Okay, so here's where 1 is. On this side, I'm only going to graph that line. Okay, you can make a dashed line all the way down and erase it later or whatever you guys would prefer. Then between 1 and 4, I'm going to graph this line. So the next boundary is here at 4. There's going to be one type of graph in there. And then beyond 4, there's another graph. Okay? How do you guys go about physically getting these graphs on the line? Do you guys always start at the y-intercept and count and then just don't start drawing until you get to the place where it works? Okay, so that's one way. How many of you guys draw the whole line and then you erase the pieces that you don't want? Okay, there's another way. How many of you guys start with the end points, like the points along the boundary? All right, so I'll show you this way as another way for us to do this, but it doesn't have to be the way that we do it, okay? So if this graph is going to end when it hits 1, one thing I can do is I can clearly get that point where it's going to end, right? So if I plug 1 into this function, 2 times 1 is 2 plus 1 is 3. So 1 comma 3 is like an end point for this function. Is it a closed-in circle or an open circle? Open, because I'm not technically allowed to equal 1. So I'm going to mark the point 1, 3 with an open circle. Okay. Now, these functions are extra special because they're lines. And for lines, how many points do you really need to draw a line? 2. And we have 1 if we put the boundary point in, right? So for lines, you can use this idea that if I just get one other point, I can draw it. So you guys have a couple of options here. You could work only this way from this point. So if it has a slope of positive 2, but I want to go to the left, right, I'd need like a negative 2 over negative 1. So one way is I can do slope from this point. I could go negative 2, negative 1. Because negative over negative still makes a positive slope, right? And then I could draw it in that way. What's another way I could get another point over here that I know this point has to connect to and get another point on the line without counting slope? What can you always do if you want to point for some graph? Sydney? Okay, so we can find the y-intercept. So this one's easy because we cross the y-axis. So that's an idea if you cross the y-axis. What if you don't cross the y-axis, but you just want to plot another point on the line? Yeah, Serena. Okay, good. Good job saying less than 1. So you could technically plug in any number you want and get a point on a graph, right? An x and plug in a y. Do you guys know why she specifically said less than 1? Then she'll make sure she gets a point over here, and she can just connect the line in this area where she knows where she's drawing it. So I can plot the y-intercept, draw the whole line. I can erase parts of it. I can start to draw it, but not really draw it till I'm in the section I need to be. Or I can plot an endpoint and one other point, and I can connect them, okay? The other point can be found, again, by counting slope from this one, as long as you're doing it correctly. Or y-intercept if you cross the y-axis, or just plugging anything in. So let's say I plugged in negative 2, because negative 2 is something that's less than 1. 2 times negative 2 would be negative 4, plus 1 would be -3. So -2, -3 would be a point on this graph, okay? Right? 1, 2, 1, yeah. And then I can connect that portion of the line, okay? Endpoints work really, really well if you have a line and you have two directions. Because again, how many points do you need to draw a line? 2. If you get an endpoint, so when I plug in 1, -1/2 times 1 is -1/2. You guys have to be okay with fractions a little bit. If you need a little scratch work, it's okay. So -1/2 plus 7/2 equals 6/2, which is just 3. So I plugged in 1 and I got 3. This time it's a closed-in point, so it just covers the point that's already there. So also detail from before. If it was an open point and then it was a closed point, there's no special notation for that. It just means the point eventually got covered up, so it shouldn't be open anymore. It should just be part of your graph. Okay? The second endpoint, if I plug in 4, 4 times -1/2 is -4/2. You can turn it into 2 if you want. I don't want to because I have to do fraction arithmetic, so I'm trying to set up. So if I have -4/2 plus 7/2, I get 3/2. So when I plug in 4, I get a y value of 3/2. So I'm going to plot the point 4, 3/2. 3/2 is like 1.5. So 4, 1.5. That one's open according to the restrictions. And there's the line that would connect them. That should match the same thing that you guys highlighted. Okay? And then for this last function, okay, if you recognize it, you should know that it's constant. It has no x in it. It should just be horizontal. But if you don't recognize it, you can, again, plug stuff in. When you go to plug something in here, there is no place to plug it in. That doesn't mean there's not an answer. It means the answer is always just 1.5. So when I plug in 4, I'm going to get 1.5. So that's now going to cover this up with a closed point. And then if I plug in any other number, say I plug in 6, again, there's no x here to plug it into. The answer is just always 1.5. So I'd get like 6, 1.5. And so this would be a horizontal line. Okay. I am not saying you have to do it this way. Can you guys please recognize that? No math instructor should ever take away anything that you know how to do. All they should do is add another idea into it that might be helpful to you. And if that idea is not helpful, but you have another strategy of doing it, then you can stick with your strategy as long as it's getting you to the right place. And if not, we just have to clarify something about that. So again, the strategies that you have, you can sketch all the lines separately and then like pick out the pieces and put the graph together like we did in the notes. You can draw the lines on the graph, erase the parts that you don't need. Okay? You can plot the endpoints and then pick another point as long as they're linear. Once we start doing quadratics and stuff, we can't just plug in lots of random points, but we can still plug in sometimes. Okay, so we have several ways that we can do this, and your job is just to pick one that you work or that you like. So I'm going to walk around real quick and make sure everybody has some way that they know how to do this. If you guys have a question about how someone in your group did it, do this for me. Tell each person your preferred method of how you're going to graph this, and then allow someone to ask you a question if they're not sure yet of which method they want to use and what might be the best for them. Okay, so do we all have a plan of attack? Okay. So we all have a plan of attack. Do we all have a way that we approach graphing this? Okay. So a couple of things to review. First thing, is this a function? Okay, so do you guys remember how to check for a function? The vertical line test for this one, yeah. So vertical line test will test if it's a function because it's basically a rule that says every x only has one y. So a vertical line checks that one x to make sure it doesn't hit more than one point or have more than one y's. So if it can pass the vertical line test, it's a function. So in this case, yes, this is. Okay. Is this function continuous? Yes, and continuous is exactly what it sounds like. Could you start on one side of the graph and draw the graph without lifting up your pencil, essentially? If you have to lift up your pencil because something is disconnected, then we call the graph discontinuous, and then it just gets that label, okay? So this one is continuous because our endpoints happen to overlap with each other. That won't happen every time with every piecewise function. So if they don't connect, it doesn't mean you did something wrong. It just might not connect, okay? All right, domain. Who knows the domain for the function? Chloe. Good. It is all real numbers, and there's two ways for you guys to check, okay? One way is to look across the graph. Any x value you pick, could you find a point that matches up with that x value on the graph? That means you could plug in that x and get a y and build a point, and every x can do that, so every x is part of the domain, okay? So the domain is all real numbers. I have a friend that teaches, and she's super fun. I'm not super fun, but she's super fun. And she wears like this like teaching apron, and she has like these random things in it. Yeah. And she has a two when she's teaching domain and range. It's really dumb. One is like Jay-Z, and one is like Spider-Man. And so then she's like, so Jay-Z is, well, yeah, maybe now should be Beyonce, but so Jay-Z is like on stage, and so like she always talks about him when she talks about domain, because she literally takes out her little puppet, and she's like, can he walk across the whole stage without falling into a hole or something like this? Then like the domain is all real numbers, you know, whatever. And then when she's talking about range, she talks about Spider-Man because he like climbs up buildings. Yep, but she actually has puppets and everything, and she teaches like calculus. I'm not like, she doesn't teach like algebra 1. Okay, so. All right, range. What is the range of our function? Summer? Good. Okay, and those of you that like the interval notation, remember the intervals always list, this is the smallest thing I can be in this category, and this is the largest thing I can be in this category. So if we're saying y is less than or equal to 3, there is no smallest thing, but the largest thing is 3. So our range would go from negative infinity to 3. And remember, the infinities always have a parenthesis because you can't actually ever reach that value. And then at the 3, you decide whether it's a parenthesis or a square bracket based on the fact, like, do you actually hit 3? Okay? And so since we actually hit 3, we would use like the square bracket. Okay? Does anybody need help with range? Because it's not super... Okay, last thing I want to talk about, and then you guys can work on the classwork, is plugging in and calculating. So let's say that I asked you guys to calculate f of 1 for this function. Okay? So they're telling me x is 1, and I'm supposed to tell them the y value that goes with x when x is equal to 1. Okay? How do I calculate that algebraically from the equation? Genevieve? Okay, we do plug it into one of the equations, and here's how we know 1. Look at your graphs, because we can answer this question from the graph, right? When x is 1, y is 3, because we have a point on our graph 1, 3. Why didn't I get 3 answers for the point instead of 1? The reason I didn't get 3 answers is because all of these would give me an answer, but not if they followed the domain restrictions that were set next to them. So all of these lines you could plug 1 into, and individually these lines have a point 1, something. But we only graphed that point for one of these where x was actually allowed to be 1. So when you do plug it in, you're actually only going to plug it in to one of the pieces of the piecewise function, and the piece you're going to choose is going to be dependent on if it's letting you plug in that x. So the first piece here only lets me plug in x values that are less than 1. 1 is not less than 1, so I'm not going to plug it into this first piece. The second piece allows me to plug in x values that are greater than or equal to 1, and also less than 4. This is where I would be allowed to plug in 1. Does that make sense to everybody? So I'm only going to do one calculation, and it's going to be with this equation, okay, to get the value of f of 1, and if we finish that, we should get 3. Okay? So is it okay with everybody that you're not just going to go like plugging crazy and plug them into everything that you see? You're going to check the domain restrictions first. Okay? Is that all right with everyone? Okay. So little review of piecewise functions. Again, why? Because we're going to like kind of crash course review all the different functions you've covered from Algebra 2 over the next few weeks. While we do them, we're going to add one new aspect, how we can stretch and compress them horizontally. And then the whole time we're doing that, we're going to keep doing piecewise functions, not just with lines. We can put quadratics, square roots, cube roots, all different types of functions in there. Okay? Is that all right with everybody where we're headed? Okay, so piecewise, again, this will be kind of like the